they have to, this is a funny word, they have to be CAD-like functions. Have you ever heard of that? Continuous from the right, limited from the left. So here's a positive CAD-like function. Continuous, this is, by the way, this is a French. Continuous from the right, limited from the left. There you go. If I come at it from the left, there's always a limit, right? It may not be achieved. In fact, at that jump point, it's not achieved. That's okay. That doesn't mean it's, we're not saying it's continuous from the left, we're saying it's continuous from the right. If you come from the right, it's constantly equaling its limit, right? And that is the limit there at the jump point, and by God, the function equals that, right? So it's from the right, continuity, from the left, limits out. So that's a positive CAD-like function. The CAD-like functions form a vector space. You know, you can see that the sum of two is going to be one, right? They also call them portable functions. I can't say this, I can say that. Continuous on the right, limit on the left. So you can't have arbitrary weighting functions. They have to be well behaved. The thing you really want to stay away from is negativity. You can't be negative. I don't want to be negative about this. Right? You want to be positive so that your integrals grow as you go to the right. You can't suddenly get into a little desert area where things start to go back down again, right? And the partition points, when you set up Stieltjes sums, if you have this continuity here, you're always picking up that lower point. You know, if a partition point breaks right there, the value of the function goes with the higher subinterval. That's a feature of CAD functions. So there, you'll learn something new with CAD. Don't forget the accents. Okay. All right. If you want to phrase the Stieltjes integral in terms of just a sum, where you have a tag partition, you can do exactly what we did with the Riemann definition. And so you set up a sum where you evaluate the function of the tag ti, multiplied by the length of the weighted length, right, from xi minus 1 to xi. That's delta alpha from xi. And then you go through the same thing, where if you magically find the partition piece of epsilon such that for any partition finer than that, your absolute difference of the sum, the Stieltjes sum, and the limit L is less than epsilon, then you say that the Stieltjes integral exists and equals L. Just like you did in the Riemann case. Okay? So that's the Stieltjes definition in terms of refinement of partitions. We have the Riemann definition in terms of refinement of partitions. And we have the Stieltjes integral in terms of these upward lower sums, right? And we had the Darbovic formulation. Okay. So, yeah, I just made some comments there. The way we built this Stieltjes integral up with a Riemann sum, basically, but we weighted the intervals a little differently, is radically different from the Lebesgue method. So people sometimes refer to the integral that we have just created here, the Stieltjes integral that we have created, sort of using the Riemann method as a Riemann-Stieltjes integral. You'll see that in textbooks about a Riemann-Stieltjes integral, this is that. And they write RS out front to indicate that it's a Riemann-Stieltjes integral. Whenever you see the word Stieltjes, it just means there's a generalized mass function. It's just not the length of the subject. That's the key there. That's what they're telling you. So that's that. All right, now. Oh, a nice thing about Riemann-Stieltjes integrals as opposed to Riemann integrals is you can be clever about picking the weighting function and preparing where its discontinuities are, so that when you create a Stieltjes sum, you actually get a series, and then you can treat series and integrals with the same theory. And I'm going to ask somebody to explain how that works with the so-called Euler-Maclaurin summation formula, which is a funny formula, a hybrid formula. It's an integral, but yet it deals with series, sort of greatest integer sort of things. So keep that in the back of your mind when you do that next week. Euler-Maclaurin summation formula. Obviously, with those two names on it, it's not new. It's well moved in 1700s. Maclaurin was a Scotsman in the early 1700s, I think. And sort of Euler lived from 1770 to 1783. So that's the time period where this was invented. But the Riemann-Stieltjes integral allows you to develop theorems like that, where you can take series and cast them in terms of treat both theories at once, very unifying. Okay. All right. The problem with some Riemann, the problem with the Riemann formulation is you don't have nice convergence theorems, which you'd like to have. Here's what can go wrong. Do you think it's possible to have a sequence of functions, and if you integrate each one and take the limit of the integrals, is it possible for that to be different than first taking the limit of all the functions and integrating them? What would you say? Based on where this is going, you probably say, I think he wants me to sing now. Right? So let's try to invent one here that screws up badly. I might need some help screwing up. This is the interval from 0 to 2. And if I have this function here, it has height 1, right? And base 2 is a triangle. So what's the area under that curve? If I go to 1/2 and 4, what's the area of that? If I go out to 8 there and go 1/4 to 1/8, or sorry, 1/4 back down to 0, what's the area under that? So if I let this be f1 of x, f2 of x, f3 of x, of course f1 of x is 0 beyond 2, f2 of x is 0 beyond 4, f3 of x is 0 beyond 8.